Okay, so thanks. So I'm Arielle Bertrou-Cantou. I'm a third-year PhD student at LESIA, and I'm working on ELT differential piston sensing and pyramid wavefront sensor, which is quite an impossible equation. So first of all, I just wanted to briefly introduce the differential piston causes at ELT. So we first have the atmospheric variation of the spider gap because of the spider thickness, which evolve at a rate, which has amplitude and evolve at a rate typical for the atmospheric perturbation. I also mentioned the low wind effect. I didn't expect such high differential piston due to a low wind effect. And then I also wanted to mention the segmented deformable mirror, which, depending on the command loop, can introduce differential piston also, because it consists in 6 independent shells. So at the moment, the preferred design, the preferred wavefront sensor is a pyramid, and I wanted to question its ability to sense differential piston. So the pyramid, so just to introduce 2 performance criteria which are well known for the pyramid. We have first the sensitivity, which is output signal for a given mode, and the dynamic. So the pyramid presents some nonlinearities and the saturation, and so I compute the dynamic being the inverse of the cubic term of the response. I also present the modulation because it will be useful later. So basically, we use modulation for. Wait a minute. We use a modulation which helps to improve the dynamic, but this is made at the cost of sensitivity. So we need to find a trade-off between both two. So now that we know how the pyramid is working, we can calibrate it. So we build a reconstructor, which for a given amount of mode it will be reconstructed by the same amount of amplitude. However, in the operation, we are working with residuals and so speckles, and this affects the pyramid reconstruction. And the mode is affected by a sensitivity loss, and here is a key issue of differential piston sensing. There is something else which is mainly composed of differential piston. So at the end, the reconstructed phase in operation is same phase with sensitivity loss, but also bias. And this bias is measured differential piston when there is no piston in the wavefront error. So basically, the pyramid can introduce differential piston even though there is no in the incoming wavefront. So we build a transfer matrix which characterize this difference between the operation and the calibration regime. And I showed that for a petaled segmented pupil, this transfer matrix actually is not diagonal. There is a modal confusion which occurs between the petal measurement and intrapetal modes measurement. And also, it is unstable. These coefficients are varying a lot. So about 30% of uncertainty. And so this is an example of what we obtain as a coefficient for the T matrix. So here is for a petal mode, and this is for another mode which is out of petal. And we clearly see here the peak, which stands for the sensitivity loss, and something very little crosstalk. However, here the measurement of the petal mode is completely lost within the crosstalk of the other modes. so the sensitivity loss, it's already tackled using optical gain compensation, but I also add a parameter which is a crosstalk strength and which will characterize this confusion in the model, in the measurement. And because of that, if we look at the differential piston evolution as a function of time, we see that we have random fluctuation of delta P around values of lambda, and this is really critical if we look at the PSF because it is splitted and in turns we get a very poor Schrell ratio. So what I wanted to do is to enhance the pyramid sensitivity to differential piston. And so I had a look at the pyramid sensitivity map to differential pistons. So we know that the petal sensing is occurring at the edges and at the tip of the pyramid, which I call the diffractive region, and which is within the range of plus minus lambda over d of the pyramid phase mask. And so to end the pyramid sensitivity, one way would be to spend more time on the edges using different modulation paths, or to add simply to add more edges to this pyramid. So the first thing I look at is the different modulation path. So I had a look at the 3 lambda over d modulation, 1 lambda over d circular modulation, but also a clover. And what we see is something we expected, is that we have really an increase in the sensitivity for 1 lambda over d and a clover, but this is made, of course, at the cost of linearity. And we see that, in fact, using a clover is very, very, the behavior of the pyramid with the clover is very similar to the one with circular modulation. And to improve the dynamic, so here we look just at the dynamic, and we can understand that the dynamic is power for a clover. So one could suggest to add more leaves to this clover. However, if we do so, then we spend more time further from the edges, and so this is made also at the cost of sensitivity. So at the end, using a clover is seems quite useless. So we just have to, we can simply play with the modulation radius to sense differential piston. However, I still conduct this study, and I looked at the sensitivity loss coefficient as well as the crosstalk for the different frequency. And so here the five first points are the petal modes, and the other are the other modes, which are orthogonal to the petals. And we see that we lose a bit in sensitivity with the clover and the small circular radius. But we have, again, we really reduce the crosstalk between the modal residuals. With that, however, for bad things, the petal sensing is still lost. After that, I ran a series of simulations for different d over r node. So d is the telescope diameter, and r node is the fluid parameter at the sensing wavelengths. And I look at the petal error, which is computed. So it is, I do this study setting aside the wavelength ambiguity problem. So I do all of this modulo the sensing wavelengths. And I look at the residuals of petal, and I also look at the entral petal residuals, which are the wavefront residuals free of island effect. And doing so, we really see that for a large d over r node, we have a divergence of the loop, which is normal because we have a very poor dynamic to sense the lower order modes. And this in turn affect also the petal sensing. But the clover, however, could be interesting if we look at using a K-bend pyramid. For instance, we have an improvement here of a factor 2 in the petal sensing using that kind of simulation. modulation, sorry. Second, I look at the varying number of edges of the pyramid. So in blue, we have the 4 faces pyramid, and in orange, we have a 6 faces pyramid. So Olivier Fauvard already predicted faces doesn't really matter in terms of sensitivity and dynamic. However, as we increase the number of diffractive regions, and we have an increase in the sensitivity of the petal modes, which are here. And this, so here the sensitivity loss due to the presence of residuals in the wavefront is unchanged. But once again, we have a gain in the crosstalk here, which is good for our purpose. And well, that's it. And I did exactly the same thing. Looking at the different T over R node, and here we clearly see, I mean, here we really have a clear improvement of the petal error using 6 faces pyramid. And also here I have a dashed line because dotted lines because this is due to the edges sampling in my simulation, so I could validate that. Because usually when you use a 4 faces pyramid, it's aligned with the grid of your phase mask. However, with a 6 faces pyramid, you have I mean, the sampling of your phase mask matter. And this caused divergence of the loop in my simulations. However, I expect that using 6 faces or even more, 8, 10, or whatever, faces pyramid, we could really have better results with the petal error sensing. But I couldn't validate that because of computation limits. So as a conclusion, well, the pyramid is blind to differential piston. I think we already knew that. But this effect is really due to crosstalk, which occurs between the differential piston and the modal residuals, but also because of the high order of the fitting. I tried to use clovers to enhance the sensitivity, but we found out that there is an impossible trade-off between the petal sensing and the intrapetal sensing. And I also had a look at the number of edges, which is quite promising, but it means it's supposed to use another hardware solution. So my perspectives to tackle first the atmospheric variation is to use, in fact, algorithm to ensure the wavefront continuity. So I think it could be MMSC method or pairing or whatever, and to tackle low wind effects. So I'm still under the shock of the talk. We wanted to use additive hardware, and we would have to use additive hardware to measure that kind of differential piston because we can't rely on the pyramid. Okay, so thanks for your attention, and if you have any question, I will be happy to answer.
Okay, yeah, thanks, Arielle. Let me check here. Do you have any question? Yeah, we have one question first, is the easiest one. How does the petal bias signal change with residua, wavefront residua, I imagine? It's a question from Byron Egler.
Then the larger the residual and the larger the crosstalk you have. So for bad seeing, the residuals will create a kind of noise in the measurement of the petal, and this crosstalk will be, in fact, dramatic for petal sensing.
Okay.
So that's why I presented, in fact, curves depending on D over R node really understand why it's important to work at. I mean, if you want to use the pyramid to do petal sensing, you have to work in small d over R0 R0 regime.
Okay. Another question from Carlos here is, did you study the case of an axicon limit of an axicon, say, so where you have an infinite number of faces in the area kind of cone? Yeah. And
if you have an infinite number of faces, then you don't have edges.
Yes.
So.
Yeah.
So I think maybe a 24 faces pyramid would be interesting, but as I said, I have computation limits at some point. So
yeah. So I'm jumping in directly. Yeah, but the axicon has been used for wavefront sensing, right? So I'm not saying it's more sensitive than the pyramid with an increasing number of edges. But I'd like actually to see numbers on that. It just seems that if the number of edges keeps increasing, then somehow the axicon would be the upper limit, right? But then we're in that situation that we have no edges. So yeah, I don't have a very good understanding myself of when is it that the limit kind of breaks away from this simplistic reasoning. But it would be nice to.
I didn't have a look at the limit. I think, I don't know. But yeah, to me, the axicon will not be able to sense differential piston, except at the tip of the axicon. Because you really want your PSF to be splitted to be able to mirror differential piston, to be splitted at the edges.
Yeah. So in a sense, yeah, okay, I don't want to take too much time. Yeah, maybe I write it in Slack. One last question I may have for you is, so what you gave here values of d over naught, and you differentiate, interestingly, the behavior depending on this d over naught. But I assume the simulation, did you run this simulation in closed loop so that in the end what matters, not the seeing value, but more the residual? And in case, would you be able to say what was the residual when, your flower-like pyramid is working better than the circular pyramid?
So yes, I run this simulation in closed loop, but I think I didn't really understand what you wanted to know.
So basically, what will be the wavefront residual, where more than the value? What is the wavefront residual that will create this difference between the flower-like pyramid and standard one? It's square, it's 10 rather square.
In fact, so here is just zero. Without considering island effect, and here I just consider the sensing ability of the reference sensor. I didn't show the overall wavefront error because at some points we have a divergence of the loop, which is in fact shown also here. But,
yeah. But here, yes, I think so. If I am correct, sorry.
But here, what's happening here, in fact, at that point, here we see this plateau because it corresponds to completely random fluctuation of the petals. So basically, what's happening is that the pyramid had more petal within the wavefront error, and so we can have divergence of the petals here, or really random fluctuations. And here we start to have a measurement at that point.
Okay, and on the left axis you have the residual of the petal error, not the total residual of the wavefront.
No, I didn't show the total error. No, because it was not not really. I didn't find it relevant in my study, but because anyway, it was really to show that we can't really rely on pyramids. So if we can't rely on pyramids, then we don't care about the overall refund error because of the pyramid.
Okay, well, thanks to Arielle, and then